So Doron, thank you so much
Thank
for
you.
Coming and providing this webinar for us. Enjoy. Thank you very much.
Okay, thank you, Oren. Okay, guys, so what I want to discuss with you today is actually beamforming and null steering. There are some of the most important techniques that we have in wireless communications, but I think this lecture is going to be a little bit different than the regular. I'm going to be on the borderline between mathematics and physics. I'm going to start with some mathematical exposition of beamforming and null steering from a mathematical point of view. Then I'm going to move to take a look at everything from a physical perspective. I want to understand what the mathematical operations that we're doing, what are their implications. Then I'm going to discuss everything from a very practical perspective, because most of the assumptions that I'm going to make, both on the mathematical part and both on the physical part, are going to be like very ideal. So I want to take everything and to reduce it into something that is very practical. I want to show you how in real life we're doing beamforming, how we're doing null steering. Then we'll do a MATLAB demo. I hope it will be a wow demo. I want to show you how we can reject something like 40 dB of SIR and totally be able to detect QAM symbols, again, in the presence of very large interference. And then we'll discuss a little bit about extensions of this theory and so on. So let's get started. So I want to start with maybe the simplest setting possible. I want to talk about an AP or a receiver equipped with multiple RX antennas. Let's say that I have 4 RX antennas and I'm receiving a station transmitting a signal. Then mathematically, the RX signal, why this would be in this case a 4x1 vector, would be the channel age. This guy also will be a 4x1 channel times S, the transmitted signal, and everything is immersed in AWGN noise. AWGN meaning additive white Gaussian noise. So in this case, this very simple case, this very like a beginner's case, the maximum likelihood detector tries to minimize the noise energy. Of course, Y minus HS would be Y minus HS would be rho n. Would be rho n. So maximum likelihood tries to minimize the noise energy. And actually, if I'm working this guy a little bit more, then this would sum up into what we call the maximal ratio combining detector, age conj y over age norm square. This would be our maximal ratio combining. We take the signal from all of the RX antennas, we combine them through age, and then we look for the closest constellation point. Okay, makes a lot of sense. I'm gathering all of the signal from all of my RX antennas, and then I'm going and looking for the closest constellation point. Hopefully, would look like that. Hopefully, my receiver would point at the signal that is being transmitted. So now I want to go a little further, and to make one small but very important step. I want to assume that my noise is not AWGN. It would still be Gaussian, but in this case, I want it to be colored with a given covariance C. So I know that it has some kind of covariance, not necessarily rho square times I. And my question, what would be the best decoder in this case? So first I want to jump to the physical part and explain a little bit, what does it mean that I have a covariance that is not Y? This means that the interference M is coming with some type of spatial signature, meaning that it has some direction. So let's say that I know C, and now I'm playing the same trick again. I'm looking for the maximum likelihood detector. In this case, I need to minimize this cost function. And of course, you can recognize this is like a Gaussian vector with a known covariance C. Most importantly, what would be the combiner? The combiner would take a very similar form to MRC, only in this case, I'm using C minus 1. It will take the form age conj C minus 1 Y over a scaling factor, which is age conj C minus 1 age. This guy is known as the MVDR, minimum variance distortionless response. I want to dive, this is very important, I want to dive deeply into MVDR. I want to start and understand the meaning of MVDR beamforming. So in order to understand, I want to take a specific example. Let's say that I have my desired user, it's denoted by D, and this guy is coming to my array with channel H as before, and I have a single interferer which comes to the array with channel G, power PG. Let's say that R is a normalized Gaussian random variable, and again I have my noise. So this guy would be interference, and this guy would be noise. Okay. What would be the covariance associated with this type of setting? Then of course it would be rho square I from the noise, and with the addition of PG, GG conj. Okay. I remind you that the MVDR was using C to the minus 1. So I want to inspect C to the minus 1. My first step, I'm decomposing C into its singular value decomposition, SVD. It would take the form of a unitary matrix, let's call this guy U, which is unitary, a diagonal matrix, let's call it D, and this is the same U, just conj. What's nice about this setting, actually you can see it, that the first column, for example, would be a normalized version of G, and of course if we're working at high INR, meaning that the interference is stronger than the noise, then of course it would correspond to the first singular value, which would be strong. Okay, and the other columns of U would correspond to the null space basis of G conj. So I have like a setting, I have G, a normalized version, and I have vectors that are orthogonal to the first one. Together they make a unitary matrix. So NG conj G equals 0. Okay, so let's try to inspect using this setting what would be C to the minus 1, and specifically I want you to bear in mind I'm thinking about C to the minus 1 in the limit of strong interference, so that the interference PG is much stronger than rho square. So let's take a look at this guy. So if C is U times D times U conj, what would be C to the minus 1? So this is relatively easy. So C to the minus 1 would be UD U conj to the minus 1. I remind you that these guys are unitary matrices, and this guy is diagonal, so I still have U. I have D to the minus 1, 1 over D1, 1 over D2, and so on, times U conj. But the elements on the diagonal of D don't have a similar power or energy. This guy is very strong. I'm at high INR. These guys are very weak. So when I take a look at 1 over Di, it reverses. This guy becomes very weak, and these guys become strong. So in total, what I have is C to the minus 1 tends to be 1 over rho square, and G conj. Okay, interesting. When the interference is large, C to the minus 1 takes this form. Let's take a look at what it means. So C to the minus 1, 1 over rho square, NG conj. Of course, if I'm plugging this guy into the MVDR expression, then because 1 over rho square appears both here in the numerator and denominator, doesn't matter at all. So what I have is, this is a scaled version of C to the minus 1. And also here, but I want to take a look at the red points here. So NG conj here would totally null out the interference term inside Y. This guy goes away. So at high INR, when the interference is much larger than the AWGN noise, the MVDR projects Y onto the null space of G and totally nulls out the interference. I want you to take a look at things from a slightly different direction, but I think an extremely important one. Because when I inspect this expression, what I understand, it's the same thing as saying, you know what, Doran, take y, project it on ng, so I'm computing ng conj y, take age, project it also on ng, so I have ng conj age, and now what I've done by this projection, I totally nulled out the interference coming from direction g. And the optimal solution, the MVDR tells me, okay, first take care of the interference, remove it by projecting with ng, and then proceed as regular with MRC processing. So this guy is MRC. But it is MRC employed or applied to the signal after we remove the interference using the null space basis of G. Very interesting. So every strong interference source, essentially, if I'm like trying to extend this result, would take away one RX antenna, because now this guy, if I started with 4 RX antennas, after I'm projecting onto ng conj, I'm reducing by 1 degree of freedom. I have essentially only 3 RX antennas. So if I have 4 RX antennas, if I take care of 1 interference source, I have 3 left. Take care of 2 interference sources, I have 2 left, and so on. So in general, if I have NRX antennas, I can mitigate up to n-1 interference sources, assuming that I'm trying to detect a single one. Okay, it makes sense, right? It makes sense. Okay, so after we have some understanding of what it means to do MVDR, what it means to null steer, to create some nulling in a specific direction, like this is more like a mathematical direction. I'm trying to be in the null space of a vector. Now I want to turn into something that is a little bit more physical. I want to like shift my attention from the mathematical point of view to the more physical point of view. So now let's say that I have a unified linear array. This means that I have a bunch of n antennas that are equally spaced over a line. Let's say the separation is d, and make it even simpler and classical. D equals half lambda, over 2, and everything is omni. And now I have a specific STA transmitting a signal S of t, arriving to the array with direction of arrival theta. This is my DOA. And I have only one path for simplicity. So now if I'm considering the narrowband assumption and I'm assuming that I'm in sufficiently far field, I'm taking a look at the signal that is arriving at the array. It would be a scaled version. This would be a complex attenuation. And delayed version of S. And it arrives to the array with phase shifts that corresponds to the direction of arrival. Each one of these antennas sees the signal traveling a slightly different path or distance, so it accumulates phase according to the direction of arrival. For example, if theta equals 0 and I'm arriving exactly at the bore side of the array, there is no phase shift, but of course it's different than 0, then I have phase, and this guy would be e to the minus j pi sine theta times n. Okay. This guy is called the steering vector. Extremely important. So with these very, very simple assumptions, I'm thinking about the channel at frequency f. So of course, the only thing that depends on frequency would be, or that let's say has an effect on frequency, would be the delay that translates into linear phase. And if I have a vector channel, I can employ or apply MRC. So MRC would take the form H conj over H norm squared. H conj, A conj. The exponential would be with a plus rather than a minus, and X conj n of theta. And the denominator is very simple. It would simply be A up squared times n. So in order to inspect what is the physical meaning of MRC, I'm now taking a signal coming from a different direction, and I want to understand what would be the response of the signal to this specific MRC for a signal that is coming from a different direction. So I'm using the MRC designed for direction of arrival theta. I'm using it with a signal coming from a different direction of arrival phi, and I'm taking a look at the response. Specifically, what I'm interested is in the absolute value, in the magnitude of the response that depends on phi. So what I see is that everything actually depends on the inner product between the steering vector at theta, for which we are designed, and the steering vector at the actual direction of arrival phi. So if I'm plugging in the expressions of the steering vectors, what I see here, this guy here, takes the form of a geometrical series, the sum of geometrical series. So the solution would be a periodic sink with the argument of sine theta minus sine phi. Let's take a look at this from a graphical point of view. So let's say that I have my desired user at 30 degrees, and I have 4 RX antennas. I see, and this is like phi, this is my DOA, I see that I have a nice peak here, a nice peak at 30 degrees. Yeah? If I play with a number of RX antennas, for example, I'm using 16 RX antennas, and still the DOA of the desired user is 30 degrees, what I see, again, it's here, yeah? But what I see is that the beam width is much, much smaller. So the more antennas I'm using, the beam width becomes smaller. It's like a directional antenna that is pointing at the desired user. But it's not only a directional antenna. What's beautiful about it, it's an adaptive directional antenna. Because now if I'm considering in one case, direction of arrival of 30 degrees and then direction of arrival of 16 degrees, then I see that the whole pattern is changing. This is beam forming, yeah? I'm forming the beam. If I'm at 30 degrees, I will point at 30 degrees. If the desired user at 60 degrees, I will point at 60 degrees. So actually using the data of the channel, I'm crafting, I'm changing the beam pattern, and this is why MRC is actually an adaptive beam former, okay? Now let's take a look. Maybe this is the most beautiful thing. What happens to MVDR? So when I'm considering MVDR, I'm saying, okay, I have a desired user direction. Let's say it's 30 degrees. And I have the direction from which the interference is coming. Let's say it's 75 degrees. So I want to compare what the MRC, who doesn't have any idea about interference, would look like. And then I want to understand what would be the MVDR that knows that the interference comes from 75 degrees. So the blue line here stands for the MRC, okay? At the direction of 75 degrees, it has quite significant gain. But when I'm inspecting MVDR, take a look at that. This is the most amazing thing. Creates a very sharp null pointing at the interference source, trying to minimize the effect or the response at the direction of the interference source. Beautiful, beautiful. Okay. But now, you know, when I was first studying this subject, I remember that I was working with MVDR, and I was thinking to myself, hey, but something doesn't make sense. Because if I'm working at very low SIR, meaning that the interference is very, very large, and the signal is very weak compared, yeah? How can I have good channel estimation? How can I estimate the channel to my desired user with good quality in the presence of a huge interference? Let's say 20 dB, 40 dB interference stronger than my desired signal. How can I do that? Doesn't make much sense. And how can I estimate, how can I know the covariance of the interference and noise source? So here is actually comes into the game, I think, one of the most beautiful results in communications and signal processing. And this result actually says that in MVDR, I can replace C, the covariance of the noise and interference, with a total covariance R. Okay, so let's take a look at that. MVDR cares only about C minus 1 times age. It doesn't care about C minus 1. It cares about C minus 1 times age. And I want to inspect what would R minus 1 times age look like. So let's plug it in. So this would be C plus H conj, this would be R, because the only difference between C and R is the contribution of the signal. This would be a rank 1 update H conj. And now I'm employing the matrix inversion lemma. Very powerful tool in signal processing. I'm employing matrix inversion lemma, multiplying with H. What I see is that actually both these terms would be C to the minus 1 times H. So this guy is just a scalar. This means that R to the minus 1 H and C to the minus 1 H actually the same thing up to scaling. It means that, let's think about it physically or from like a, let's say a engineering point of view, I don't need C. I don't need to know the covariance of the interference and noise term. All I care about is the total covariance. And of course, total covariance is something that is very easy to estimate. Just doing empirically the estimation of the total covariance, like the sum of YY conj. So this guy, of course, is much easier than computing the covariance of the noise and interference term. But there is still like the big question, okay, I'm okay with the covariance, what about channel estimation? Again, in the presence of very large interference, how can I estimate my channel? And I need to do it like with high quality. So I want to take a look at everything from a slightly different point of view. I want to think about empirical NAR steering. And for that, I want to like adopt an approach that is very similar to what now everybody is doing in machine learning. And I want to assume that I have a bunch of pilots. So let's say that I have a bunch of pilots, PI, and pilots. And my question, again, very similar to training in machine learning, is what would be the combiner that takes my known measurements that correspond to the pilots and brings me closest possible to the pilots, for example, in the L2 sense, okay? What would be the combiner that if I apply to the incoming data, I get something that is very similar to the known pilots? Okay, makes sense. And then you say, okay, if I can find a good estimation that of W, a good combiner that brings my known data into the pilots, I will use it also for my payload. Okay, so I can very easily recast this problem as a least square problem. And if I have a simple least square problem, then of course I would have a very simple solution, y conj y to the minus 1, y conj p. Okay, but what is y conj y to the minus 1? Y conj y, this is actually my empirical covariance, empirical total covariance. This is like r hat. And to the minus 1, very similar to the solution that I just showed you using the matrix inversion lemma. And y conj p is like an estimate of my channel. Okay, so we get a solution using a finite samples that corresponds to the theory that I just showed you, that I can replace the covariance of the interference and noise with the total covariance. So you want to see a MATLAB demo? Okay, so I will switch to this one. Let's take a look at that. I'm a big fan of MATLAB files that are approximately, let's say, 50 lines. So I'm using, let's say, SNR of 15 dB and SIR of minus 20 dB, 4 RX antennas. I'm using only 10 pilots. Again, we discussed earlier about what would be the number of pilots that are used in order to do empirical calculation. So I'm only using, say, 10 pilots, and the number of payload signals, of course, is arbitrary. I'm considering direction of arrival of 30 degrees, and this would be my steering vector that corresponds to that. Let's start running with that. I'm considering interference that comes from minus 50 degrees. And this would be the steering vector that corresponds to the interference. I have pilots, and these guys would only be a vector of length 10. This is just like random QPSKs, and another one, a very long vector of payloads, which is not very interesting. Okay, we generate the signal. This would be a totally random phase that I'm using for my incoming desired signal. So Y desired would be the component that corresponds to my desired signal. I'm adding noise, creating the noise, and also the interference, adding everything together. This would be the addition of everything together into a single matrix. So the key point, I'm taking the chunk of Y that corresponds only to the pilots, yeah, and computing the least square solution for W, okay? Now, in order to have something to compare to, I'm using like the geniated MRC, and let's take a look at what would be the solution of the MRC at minus 20 dB SIR, total garbage, okay? We have total garbage. Now I'm considering the estimation that is based on my empirical beamformer S hat, and let's take a look at what this guy gives us. A little different, right? A little different. And again, I'm at minus 20 dB SIR. Take a look. The blue one is MRC, again, geniated MRC, not familiar with the interference. This guy is my MVDR solution, but the empirical beamformer, actually, I know nothing. The only thing that I know is just the pilot. I don't know anything. Yeah, the only assumption that I've made at the receiver is only the existence of these pilots. Now, the second thing that I want to do, I want to like take a look at the response of the classical MRC and the empirical MVDR. So let's take a look at that. Just let it run until the end. Okay, beautiful, beautiful. Okay, so the blue one would be my MRC. I have a signal at 30 degrees, so of course the peak would be at 30 degrees. I have an interference source at minus 50. MRC totally unaware of that, so of course the gain here is pretty substantial. Now let's compare to my empirical beamformer. This would be the red. Still a very good response, 0 dB at the desired user. Doesn't know that the signal is coming. Again, this guy only knows the 10 pilots. Doesn't know, but still puts a very good response at the location of the desired signal, and puts a very deep null at the location of the interference. Okay, so I think I want you like to remember this very important figure. I'm capable of rejecting a lot of interference, and I showed you I can have a very good detection at minus 20 dB SNR. Let's take a look at what happens. Again, just play with it a little bit. Let's clear everything. Let's move to, let's say, minus 40 dB. So now the interference is 10,000 times stronger than the signal. Let's take a look at that. Okay, very good response. Let's take a look at the detection. Total garbage for the MRC, of course. Now, guys, isn't that great? This is minus 40 dB. I know only the pilots. I didn't tell my beamformer anything about directions or any physical entity like that. Only known pilots, and I have this beautiful thing. Let's make things, again, a little bit more interesting. So I want to maybe go and put my interference much closer to my desired signal. Now I'm at 30 degrees of the desired signal and 27 degrees of my interference source. Now, I think you can agree with me that the situation is very bad. I'm running this guy. Okay. You see that it's trying to put a null on the interference source. Of course, I have noise amplification that is very evident from here. Now, when I'm taking a look at my detected QAM, QPSK, this is already something that is, I think, almost impossible to detect. What can we do? So one thing that we can do, for example, is to move to a situation when we have more RX antennas. So let's move, for example, to 8 RX antennas instead of 4. And in order to have good overdetermination, I'm moving to 20 pilots, and let's try it like that. Again, minus 40 dB SIR. Let's take a look at this tiny guy. Amazing, amazing. Minus 40 dB SIR, and the separation of only 3 degrees between the desired signal and the interference signal, and I have this picture at my demodulator. And the only thing that I've been using is 20 pilots. So I want you guys to have this. Picture in your mind to understand the strength of empirical null steering. So many of our communication systems, they're interference limited. Yeah, you can ask Andrea Goldsmith. She wrote it in her book, a very famous saying. Most of the systems like LTE, like 5G, like Wi-Fi, interference limited rather than Boltzmann noise limited. So of course, beamforming and null steering play a very, very important role. And at Huawei, actually, I'm responsible for all the enterprise Wi-Fi products, and we put a huge emphasis on beamforming and null steering in our product. The effect of null steering, I just showed you, minus 40 dB, only 3 degrees of separation between the desired user and the interference, and the effect is amazing. The effect that we have is amazing. So in this discussion, I was focusing mostly on the RX side, on receiver beamforming, but actually most of the ideas that I was portraying here, they can be readily used also for TIC. So instead of MRC, I can use MRT. I can just point the signal in the desired direction. I can use null steering at the transmitter, and this is like the basis for downlink multi-user MIMO. I can discuss with one station and put the null in the direction of all other stations, and so on. I discussed here, again, for simplicity, a single desired signal and a single interference signal, but actually I can work with multiple. For example, if I have 8 RX antennas, where's my 8? If I have 8 RX antennas and I'm receiving 2 desired signals, I can still reject 8 minus 2, meaning 6 interference signals. So the capability, or I can extrapolate everything also to multiple signals, and of course this is extremely important. One thing about the relationship between everything that we've just said and OFDM. So actually, the model that I was using, that means y equals hs plus g times r with some scaling plus rho n, this model actually is relevant on the subcarrier level of OFDM when everything is synchronized, when both the signal that I'm trying to detect, S, is synchronized time and frequency to the receiver, and both the interference is synchronized. And actually, when everything is synchronized, then H and G, in contrast to what I was showing you before, which was like a very simplified physical situation, each one of these guys can be made of multiple paths. There is no restriction in synchronized OFDM. H can be a product of multiple paths, and G can be made of multiple paths, so this is very important. This means that in synchronized OFDM, if I have 8 antennas and I'm receiving 2 signals, actually I can reject 8 minus 2, 6 interference sources. And of course, this is very important. But when the synchronization is compromised, meaning when I don't have time and or frequency synchronization, actually the only thing I can do is to reject, in the case of a single desired signal, n-1 path. This is a very, very big issue. So in cellular systems where I can align in time and frequency my desired signals and my interference signals, I can reject n-1 interference sources. For example, in Wi-Fi, when the desired signal and the interference signal are not synchronized usually in time and frequency, I can null out n-1 interference path. This means that when the system is not synchronized, we need to work a lot harder in order to have good nulling. So I hope that this presentation gave you a good understanding of both the mathematical fundamentals of beamforming and null steering, both the physical aspect. I want you to see the beams, to see the nulls from a physical point of view. I think the MATLAB demonstration showed you it's a very practical thing. It's not like you need to have an ideal estimation of C, an ideal estimation of H. Even with 10 pilots, when I'm using 4 RX antennas, I can reject a huge amount of interference, minus 40 dB SIR, for example, and if the separation between the desired station and the interference is very, very small, then maybe I will need to go to a larger number of antennas. Of course, more antennas meaning that I can have narrower beams. So finally, beamforming is 1, beautiful, 2, very, very effective, and very, very practical. So you guys who are like experts in modem, in communication, who actually build communication systems, I greatly encourage you to explore this avenue. Beamforming and null steering can make the whole difference between a system that doesn't work with interference to a system that works beautifully with interference. Questions, anybody?
Does the same apply for TX?
Yeah. As I said, many of the ideas that I was discussing here, they can readily apply to the TX. For example, I can use MRT, maximum ratio transmission, instead of maximum ratio combining, and create a directional beam at the direction of the desired user if I know the channel. And of course, in many of the advanced communication systems, I have some feedback that allows me to also at the transmitter to know something, a partial channel knowledge about the channel to the desired user. And if I also have knowledge about the channel to the interference source, for example, like in downlink multi-user MIMO, as I wrote here. So if I know the channel to both the desired station and also to the stations that I don't want to interfere to, like downlink multi-user MIMO, so I can also do null steering the transmitter. Actually, it is usually easier because in these cases, I have very good channel knowledge of my intended receivers. Is that clear?
Yeah.
Great. Any other questions? Guys who ask questions have a better chance of winning the high-value prize that Oren was mentioning. Okay, guys, so if there aren't any more questions, then thank you very much. It was a pleasure to discuss this, from my perspective, beautiful topic with you. And if questions arise later, you can always contact me or Intelligent. Thank you very much.